want to talk about Burnside's theorem, namely that every group of order Q to the A, Q to the B, is not simple. To be precise, that there's no proper norm, non-trivial proper norm subgroup. So why do we care? Good question. Largely, it's because groups decompose as normal subgroups. And this is used a lot in the classification of finite groups in the 20th century. And this theorem in particular was proven in the early 1900s using representation theory. And so we'll look at how representation theory can be a useful tool. Purely group theoretic approach was not developed until the 70s. It is way beyond the scope of anything we can do. I can do it. Maybe some of you, I don't know. So first of all, we're going to define a representation. So it's just a group homomorphism from G to the general linear group of some vector space. We're going to consider G finite and V to be a complex vector space. And also a few things. So we say that G in a group acts like a scalar if the representation of G is just C times the identity matrix. And being a homomorphism, every non-trivial representation of a simple group is injective. And we can also define an algebraic integer. This is just some complex number such that a monic polynomial with integer coefficients evaluates to 0. Now, we're going to denote this by z bar. This set forms a ring, and roots of unity are in algebraic integers by definition. And we also have a character of a representation. Put this right here. The character of a representation is just the trace of the matrix. And a few important properties of character. The character is what allows us to do all of the magic representation theory. It's conjugate invariant just because trace is conjugate invariant on a change basis. So the character has some conscious class C is equal to the character of the group element in that conscious C class. The character of the identity is just going to be equal to the dimension of V, since it being a homomorphism means that the pi of E would equal that identity element. Trace that identity is the dimension of the space. And now, these are some facts. I don't know how to prove this, but you got to take my word for it, that the character of the conscious class divided by the character of the identity times the order of the conscious class is an algebraic integer, and the character of any group element is an algebraic integer. I can give an oral explanation of this one. You can choose a basis such that it's diagonalizable with Jordan box 1, and then it being a finite group means if you take it to the order of the group, then each element on the diagonal has to be a root unity, and so the sum of roots of unity is a root unity. This is a ring. Okay, and now we need a few key facts to make proving this theorem feasible. So first of all, if G is not isomorphic to Z mod P, and there exists a non-trivial group element in G that acts like a scalar, so pi G is Ci, then then G is not simple. Right, this follows just because pi acts as a scalar, pi can use with any matrix. More specifically, it can use with any other pi G pi H commutes with any other representation of a group element. And then just by properties of homomorphisms, we get that by HG equals. Alright, and this condition either means that G is in the center of the group, and the center is always a normal subgroup, and because it's not isomorphic to Z mod P, that center is not the group itself, so we've produced a proper, non-trivial normal subgroup. Or HG is not equal to GH in general, but then this would mean that pi is not injective, and since it's not injective, the kernel of such a representation is a normal subgroup. Okay, now I'm going to switch boards here. Now, get our next important fact. So pi g acts as a scalar if and only if the absolute value of the character g equals the character identity. So this follows because there exists a basis in which pi of g is diagonalizable with Jordan blocks of size 1. So if you choose such a basis, then chi of g equals chi of e is equivalent to saying that C1, so these are the diagonal elements, and this is the trace, equals the dimension of V. And each of these are roots of unity by my previous oral explanation. And so by the triangle inequality, we would get that this is less than or equal to C1 plus Cn, but since these are roots of unity, these are 1, so this would be the dimension of V, and so this has to be a strict equality, this right here, which just implies that all Ci are equal and equal to, all Ci are equal, and so pi g is a scalar. Okay, that's useful because we have that pi of g equals pi of e if and only if pi of g divided by pi of e is an algebraic integer. I do not have time to prove that whatsoever, but it follows from Gauss's lemma using the minimal polynomial of chi of g over chi of e over rationals. For now, just take this as a black box. Okay, now we get to the important proposition. And this will imply Burnside's theorem. So if the order of g is q to the a, q to the b, I have to erase this, I'm so sorry. That's okay. Just remember, this is the 2026 TRP.
It's a big group.
Yeah, there exists a character and a group, a non-trivial group element, such that pi g over pi e is an algebraic integer. Okay, and I hope we can see that if this is proven, then Burnside's theorem will follow from our facts. This implies this, implies this, that, and then Burnside's theorem is proved. So if we can prove this, we prove it. Okay, so by silo, we have a normal, we have a subgroup of order q to b. Now every prime power order group has a non-trivial center, so there exists g and e in the center of this subgroup. Okay, now note that the centralizer of this group element is a subgroup G, and H is a subgroup of the centralizer just by construction, which would imply that the order of the centralizer has to equal P to N through the B for some N. It says H has to divide the order of Z, or the centralizer of G, which has to divide the order of G itself. So if we consider the conjugation action, we have that the orbit of the conjugation is just a constant class, which we call C. And the stabilizer, well, that is just the center of G after we're rearranging. And so by the orbit stabilizer theorem, we have that the order of C equals order of G divided by the order of the centralizer of G, which is a conclusion shot. So block shot. Which is just going to be P to the A, Q to the B, divided by P to the N, Q to the B, and so we constructed a conjugate class that is P power order. Which goes to this blackboard. I'm going to erase our definition. So, now we have that C is a prime power order. So what I want to show now is that the character, the identity element, you can produce a character that is not divisible by P. Hence they are co-prime. So, as a lovely result from representation here, we have that if we sum over any constant class, or if we sum over the characters of constant classes, which in this case will apply to C and E, which are distinct because G is not trivial, this has to equal 0, which is equivalent to saying that once you pull out trivial representations and representations where where chi of C equals 0, so we're just going to call these chi s. Equals 0. And now suppose there's no representation such that P does not divide chi of E. Then that means that chi of E divided by P is an integer. Specifically, it's an algebraic integer. And so we can take this and divide it all by P. So we do 1 over P plus the sum over chi s of chi of C, chi of E, P is 0. And now we can recall from our facts, I erased one of the important facts, but this guy is an algebraic integer by assumption. This guy is an algebraic integer by properties of character, and 0 is an integer, so it's an algebraic integer. And algebraic integers being a ring means that 1 over P has to be an algebraic integer. What could be wrong with that? So 1 over P being an algebraic integer means that there exists a modic polynomial such that it evaluates to 0 at 1 over P. Well, multiply everything through by P over N, P to the N, and we get let me bring this one over, and then we have that this equals -1, but this guy vanishes mod P, so that is not possible. That's a contradiction. So there has to be some character such that chi of E is co-prime with the order of C, the constant class. And I won't erase more defects, but I won't erase the names. Okay, so since they're co-prime, there should be integers I and j instead. Alright, this just, hopefully you take an abstract algebra, that's just a basic consistency class, which is non-trivial, just because G is non-trivial. So we have that pi of G over pi of E is an algebraic integer. And now everything falls, right? The proposition holds, and thus, from fact 3, this being an algebraic integer implies that the order of the character of G equals the character of the identity, and then by fact 2, that implies that I of G is a scalar, and then by fact 1, which I erased, but that's okay, that implies that G is not simple. So, thus, every group of order P to the A, Q to B is not simple. And that's all.
Okay. Let's thank the speaker.